Hey guys, today we're going to do a lecture series video on gas tungsten arc welding or TIG welding. This is my favorite process. This is what I did as a welder for many years. I worked for a fabricator for about 7 years that did a lot of TIG welding. They built vacuum chambers and valves, pressure vessels, things like that. So really I got my start in the welding industry, mostly TIG welding, among other things. And I really fell in love with this process. It's just a super clean, precise process. And I just really gravitated towards this process. So it's going to be fun for me to go through all the different elements here and kind of break it down. So this is to just teach you kind of the theory behind it, and then I'll have another video that's a little bit, that'll talk about the theory as well, but it's going to be a little bit more focused on the actual hands-on portion and welding a few relatively simple joints to get started with. So we'll just start with the theory. So this is gas tungsten arc welding, so that's the kind of the official name that we use now. It's a inert gas shielded process, so it uses inert gas, which means that doesn't actually add anything. The gas itself doesn't add any elements to the weld pool or to the electrode itself. Because we're using a non-consumable tungsten electrode, which actually carries the current to melt the base material, we don't want a reactive gas like we use with MIG welding or something like that. That might add some elements both to the electrode itself and contaminate it, but also to the weld pool. Because one of the advantages for gas tungsten arc welding is that we can use it to virtually weld any material, whether that's carbon steel, aluminum, stainless steels, all kinds of different alloys that can be very susceptible to contamination and things like that. We just want an inert gas that will just shield that weld area from the atmosphere and keep everything nice and clean and not actually add anything to that base material. So that's the basic idea of what the process is itself. I have a little diagram here of a typical setup with a constant current power source. So that just means that no matter what the welder's doing, the power source will be trying to keep that current the same. Whether you're varying your amount of arc spacing between the end of the electrode and the base material, the power source is going to try to keep that current or amperage constant. So just like a stick welder, we use a constant current power source. So there's only really one parameter that we're going to be able to adjust, and that's amperage for the most part. Amperage, there are some other things that we can adjust, but it makes it very simple. If we want more heat, we just turn up that amperage. If we want less heat, we turn it down. Okay. So as far as types of current, with TIG welding, we're either going to be using direct current or alternating current, depending on the type of material that we're welding on. For steel and stainless steel, our polarity will typically be DCEN. Direct current electrode negative. And then for materials like aluminum, magnesium, we'll be using alternating current. There are very few situations where we'd be using DCEP for TIG welding because it puts a lot of heat onto the electrode, which I'll explain in a minute. And so there's very few times that we'd use DCEP, but sometimes we use it where we need a lot of cleaning action on like aluminum or something like that. So DCEN for carbon steel and stainless steels, so basically steels, and then for AC would be aluminum. That's alternating current. So the type of polarity that I have drawn here would be a DCEN polarity. So that's direct current electrode negative. So that tells us right in the name electrode negative that our electrode, or in this case, our TIG torch, with the electrode in it should be connected to the negative terminal. And then that would mean that our ground clamp is connected to the positive terminal, okay? So that completes our circuit, our welding circuit, by having those, that ground clamp connected. Now, as far as polarity, what actually determines where our heat will be focused is the movement of the current. So the current will always move from negative to positive. So in this case, since we have our torch connected to the negative terminal, our current is going to be traveling in this direction. It's going to travel through the torch, out the electrode, and it's actually going to make the jump from the end of the electrode to the surface of the plate, which is the other side of the circuit here, and then it will make its way back towards that positive. So current always travels from negative to positive, okay? So that tells us where the heat will be focused. Because this current is making the jump from this side of the circuit to the other side, it's going to generate resistance on this side. So that means that about 70% of the heat will be in the base material with this type of polarity, DCEN. So that means that most of our heat is focused in that base material with DCEN. And that's one of the reasons with this type of polarity, with TIG welding, we get really good fusion. It's a very good, high quality welding process in terms of being able to ensure that we're getting full fusion. Whereas we look at some other types of welding processes, such as like short circuit GTAW, with the polarity that would be reversed, DCEP, where the heat is focused in the solid wire electrode. It's not as efficient because we lose a lot of heat that way, and it just creates an environment where lack of fusion is a possibility. So this is one of the reasons why DCEN on carbon steel, stainless steel with TIG is such a reliable way to ensure good, high quality, strong welds that have really good fusion through the joint. Okay, so that's a basic setup for DCEN polarity. Alternating current, I'm not going to get into too much today. I just kind of want you to know about the differences there between the two different types of material. But basically, alternating current is kind of what it sounds like, where the current actually alternates directions. And so then that gives us the benefits of both the types of polarity, where we get the penetration of the DCEN side, and then we get what's called the cleaning action of the DCEP side on materials like aluminum that have an oxide layer that we need help cleaning up. So again, I'm not going to get too much into that, because if you're just getting into TIG welding, that can kind of get into the weeds and just make it more confusing to start off with. So we'll just stop there in terms of polarity and different types of currents. But I'll probably follow this video up later on with a specific AC welding on aluminum video on TIG, because there's a lot of really cool things that you can do with the settings, with the AC sine wave, to really get some different things out of your arc and for different situations. So we'll get into that later. Okay, so this is the basic setup for TIG welding. And again, some of the advantages of TIG welding are super high quality, clean welds. You can see everything that's going on in that weld pool because there's no flux. There isn't a lot of fumes being generated, which is another plus. You are a little bit closer in there welding with TIG welding, so you can actually be, you can get more fumes that way. So especially on things like stainless steel, you want to protect yourself with the respirator, make sure you have good ventilation as always. But that is one of the advantages, is that you don't have those fumes and you are up close, so you can really see everything that's going on in that weld pool. So especially for like open groove welding or really high, high-end critical type joints, it can, you can really ensure that you can see everything that's going on in that joint as you're welding. So really high quality, clean welds. Another advantage that I talked about before is that you can weld on any type of material, any type of alloy can be welded through TIG welding. Some of the disadvantages of TIG welding is that it's a very slow process in terms of your inches per minute that you're being able to weld at, because it is a slow process. It's a manual process. You're adding filler metal by hand, and it's just fairly slow. So it really brings down your deposition rate in terms of how much metal you can put down at any given time. So that is one disadvantage. It's not really a high production type process. The other disadvantage, like any gas shielded process, is that you start to add some other elements there in terms of equipment. It can lead to other things. It's not as usable out in the field because you have to bring a gas bottle with you, depending on not whether you're using a air-cooled torch or a water-cooled torch. You might have to have an intercooler for the torch. So it just can add other things to what you need to actually get started welding. So and then also it being a gas shielded process, you have to be protected from the elements. If there's any type of wind or even a fan that's blowing in the weld area, that will blow away your shielding gas, and it will cause contamination and porosity in your weld. Okay, so those are some of the advantages and disadvantages. It's a great process to weld in the shop on higher end alloys and things like that, or just if you want to weld to have a really nice appearance, it's great for that as well. For all you Instagram welders out there, you all know already about GTAW and how to, put some nice welds out there that look Instagram worthy. So, so that's about it for advantages and disadvantages, and we'll get into some of the other elements of the process like technique, electrode classifications, filler metals, and stuff like that here in a second. All right, the other part of the basic setup is how we want to initiate the arc. So we have a couple different options. We have basically where we use either what's called lift arc or scratch start, where you make contact with the material and you lift up and it will initiate the arc. Then, we weld along. When we get to the end where we want to terminate the arc, we just lift up very quickly. Machine will sense that increase in the resistance and it will shut the arc off. That is more typical in the field where we might not be able to use a remote amperage control like a pedal here. So that is something, especially for like pipe welding, lift arcs used a lot, and again, welding out in the field where maybe we don't want the extra components. But for shop welding, a staple would be a pedal or a remote amperage control. And basically this will not only initiate the arc by pressing down the pedal, but in most cases it will also give you a remote amperage control, meaning that you set the amperage at a certain amount. When you first press it on, it will start at the low end of that, maybe 5-10 amps. And then as you depress the pedal all the way down, it will go to the maximum that you have it set for. So that's a pretty much a staple of shop welding. That way you have some amperage control as you're welding. You can start off a little hotter to get that weld pool started, and then you can back off of that as you get to the end of the weld where the material starts to heat up and you maybe get a little bit of that weld pool starting to get a little bit more wide. You can start to back off of your amperage. It also gives you a little bit of that crater control at the end. When you get to the end of the weld, you can add a little bit more filler metal and you can back off of that amperage slowly to reduce the appearance of a crater dimple from it shrinking very quickly as it cools. There's also some different settings that you can do on your pedal. There's on most machines, there is both just a straight amperage control and a 2-touch hold, which means that instead of being able to control the amperage, you just hit this pedal once. It's going to increase to the peak amperage that you have set, and then you hit the pedal again to terminate the arc. So that'd be a two-touch hold. Different types of welding machines call it different things, but typically you have a straight amperage control and a two-touch hold. Okay, there's also sequencers and stuff like that that you can use to individually adjust how fast amperage comes, how long it stays at a specific amperage, if you want it to drop down or not at the end, and stuff like that, but we won't get into that too much in this video. So remote amperage control or pedal, or lift arc and scratch start. All right, so now let's talk a little bit about technique. So one thing that is very, very important is the distance in between the end of the electrode and the weld pool, and this is called your arc gap. So let me back up a second, because I just wanted to point out that these three things, arc gap, travel angle, and travel speed, are three things that you should always be paying attention to, no matter what process that you're learning, or that even as you're working with it. I had a mentor of mine that used to walk around the shop, and he was used to be in the Marines, so he would walk around the shop yelling like a drill sergeant would, or something like that. I know that's the wrong term for it, so sorry, military guys. I know you'll comment on that. But anyway, he used to walk around the shop yelling these three things: arc gap, travel angle, travel speed, gentlemen. These are the important things that we need to pay attention to. And at the time, I kind of thought he was crazy, but then after a while, I'd be beating my head against the wall on a specific weld, just couldn't understand why something was happening with that weld profile. And it would always typically be one of these three things that I was doing wrong that would be affecting the profile. So just keep that in mind. But in terms of GTAW, we want a small arc gap. We want this, the end of this electrode to be as close to this weld pool as possible, with able to still add our filler metal and not have it actually touch the end of the electrode. We don't want to bury this electrode in the weld pool, which will contaminate the electrode and also create tungsten inclusions. So we want to be careful of that, about 1 to 2 times the electrode diameter, which can come in various diameters. As your electrode gets bigger, your arc gets bigger, and in terms of diameter, and so then you can get away with a little bit more of a gap there. And of course, it depends on how large the filler metal is as well. But you really want to keep that as close as possible to maintain as much control as you can, not to lose any of that current. And also, as you move this electrode further and further away, that arc cone gets wider and wider, and it gets more erratic, starts moving around on you. And then you also lose your shielding gaps as you move further away. So you want that to be nice and tight. And you also need to be able to see what's going on. So, if you have it really close, you're going to need to be able to move your head to where you can see exactly what's going on, with your arc spacing and what's going on with the weld pool. Now you notice that this work angle is about 90 degrees. So the angle in this flat position, our angle is 90 degrees on either side, straight up and down. In this flat position, we wouldn't want to have this work angle going off to either side, which would push that weld pool off one side or the other. We would want it to be straight up and down so that we have a nice even sized weld pool and we're not shifting that weld to either side. The next thing that we're talking about is travel angle. So this is in relation to our direction of travel. So in this case, we would be traveling this direction. We're welding along this way, and we always use a push angle with TIG. Okay, we're never dragging with TIG welding, we're always using a push angle. Our shielding gas is coming out ahead of the weld, and if we're using 100% argon, that's heavier than air, so in this flat position, it would just kind of sit on the surface of this plate and give us some really nice shielding. But we want to use a push angle so that our shielding gas can get out in front And it also just gives us the best profile. We're adding our filler metal from the front of the weld pool as well. So in terms of travel angle, we want to make sure that our angles aren't too extreme. We don't want to use too much of a push travel angle, because then that just directs our arc and our heat out the front rather than, you know, into the base material. So we want to make sure it's about a 20 degree off of 90 push angle, so that we're directing the heat down into the base material, into the weld pool, and not towards our filler metal. Now, one of the other advantages I forgot to mention about GTAW is that we can weld autogenously, meaning without filler metal. So we don't even need filler metal for, you know, very thin materials, stainless steel. We do a lot of autogenous welding without filler metal at all. So it's not necessary all the time that we actually use filler metal. I think it's a good idea if you're just starting out to get an idea of how to push the weld pool along the plate without filler metal to start with before you start trying to add filler metal. But a lot of times that's what we're using is filler metal on thicker materials. So we want about a 20 degree push angle, and then the filler metal approximately 90 degrees to the electrode in terms of, you know, how those two are going to meet up. And that's relative depending on what type of joint you're doing, what type of position you're doing, and all that kind of stuff. You just don't want too extreme of an angle this way or too extreme of an angle with your electrode. I'm sorry, your filler metal. Your filler metal, the angle of your filler metal will actually determine how much filler metal you're actually adding. So the higher you go with this filler metal dipping into the weld pool, will actually add less filler, because you're taking a smaller cross section of that filler metal. As you put it flatter, you're actually adding more, because you're able to dip in more of that filler at a more gradual angle. So just keep that in mind. But to start off with, about 90 degrees to the electrode itself is where you want to keep it. One other thing that I'm going to mention, and this kind of relates to travel speed, which it should always pretty much be slow, right? That's what I see a lot of beginning welders, no matter what. They're always typically going too fast for any process. But TIG welding, you really need to get that weld pool established first. And you have to keep in mind that this process can be used autogenously, okay? The torch and the electrode is what creates the weld pool, okay? It is not the filler metal that creates the weld pool. And why I'm stressing this is that I see a lot of welders, when they first start off with TIG, they take the filler metal and the torch and they start trying to melt the filler metal onto the plate. Okay, that's not what we're doing with TIG welding. We are creating a weld pool with the torch. Once we get a weld pool started, then we are adding the filler metal to the weld pool. The weld pool is what melts the filler metal, okay? Otherwise, you're just melting metal on top of metal, and it's just a mess, and it doesn't really coalesce those two materials together, okay? You have to start the weld pool with the torch first, then add the filler metal to it. Okay, so when you're first starting out, I really do recommend just getting a weld pool started with that nice 20 degree push angle, and just try to push that along the plate to get started. Try to do that consistently and have a consistent size of that weld pool as you go across of that weld bead, as you go across just autogenous welding with no filler. Then as you get comfortable with that, and you can keep that angle all the way through, then you can start to add filler to the front of that weld pool as you go forward, okay? Travel speed slow, make sure you get that weld pool established before you start moving forward, and try to keep all that consistent as you're moving forward. And that is the basic technique for GTAW. And just keep in mind that it doesn't matter whether you're in the flat, the horizontal position, going vertical up. you're always going to try to maintain this 20-degree travel angle. So even going vertical up, we're still going to use just a slight push angle as we go up, okay? And we're never going vertical down with TIG welding, okay? Always vertical up. That's why you see even in pipe welding, they're starting at the bottom of the pipe and going up on both sides. They're never going vertical down with TIG welding. All right, so now we're going to go over the different types of torches and the different type of components for the torches. So we have two different types of torches. We have water-cooled torches and we have air-cooled torches. Water-cooled are typically used more in shops where you can have extra equipment like an intercooler, which will be running the water through the torch to cool it down, and this gives you a longer duty cycle. You can weld for at higher amperages for a longer period of time, but it is a little bit more cumbersome, having the extra lines there. But this is the the industry standard typically for shop welding. Then for a gas shielded torch, they're a little bit more bulky typically because of that lower duty cycle. That way the components are a little bit larger, can take more heat. But this is a staple for field welding out in the field because now we just have a gas line and a current line going into the torch. And so this is what we're typically using in the field. So all the components for a gas-cooled or air-cooled torch will be larger to take more heat than a water-cooled torch. So we have all the components here for a torch itself. We have the torch body, ceramic cup, collet body or gas lens, the collet itself, the tungsten electrode, and the back cap, which I'll be going over today. Okay, so for a torch body, we have different types, like we were just talking about, gas air-cooled versus water-cooled, and then there's just different styles. Some of them are flex head. This particular one is a crafter series, which is kind of like a triangular shape to it, which I used these for a long time when I was fabricating, and I just really like them. I like the different angles that are on the handle. Gave you a variety of different grips that you could use out of position. But there's other types that I've used over the years that I like just as well as these. But this is pretty typical of a water-cooled torch body. Okay, so from there we have our different types of gas diffusers. So we have one that's called a collet body, which looks like this, and it's basically just a little machined piece that has holes drilled in it, and this diffuses the gas. And I mean, it's efficient and it's relatively inexpensive, but it is not the most efficient in terms of gas coverage. That would be a gas lens, which actually has a little screen inside of it that diffuses the gas. This one's a little dirty, probably didn't use some gas with it or something. But it has a nice screen on the inside which diffuses the gas, and it makes a very defined long stream of gas. So you can use a longer stick out with it. It just gives you better gas coverage. So I typically use a gas lens just about all the time now. If I'm welding stainless especially and I want good gas coverage, I'll use a gas lens for that. It does change the ceramic cup. A ceramic cup for a collet body will be a little bit more narrow because of the nature of the collet body that it's going over versus a gas lens ceramic cup is a little bit fatter. So if you're trying to get into a narrow place, sometimes you have to go back to the old reliable collet body. Also, collet body, if you're welding on dirty material, will not get clogged as easily as a gas lens, so it's something to think about. But typically we're welding on relatively clean material with TIG anyway. So our different types of ceramic cups, as far as size goes, the number on them is just the orifice opening in 16ths. So this one is a number 5, so that would be a 5/16 opening. whereas this is number 8, I believe, which would be 8/16 or a 1/2 inch opening. Okay. Now, the larger the opening, the more gas that comes out of that, the more flow you need to use, which means that it can be more expensive. But typically, the better gas coverage you get and the better color that you'll get out of your welds within reason. If you turn it up way too high, then you're going to start to get some Venturi effect where you'll actually bring atmospheric air in and get some contamination in your weld. But within reason, as you go up in the size of the orifice, you're going to need to go up in your CFH for your gas flow. Then we have the larger oversized cups, like this is a size 12 FUPA. This is a Furic cup, and I love this thing. This is how I impress my students. Get that wow factor in stainless steel welds because you get such good coverage. It just really improves the overall color. Get those Instagram ready welds to post, that's how you get that. But, for some of the alloys that are more susceptible to contamination and stuff like that, these larger size cups with a gas lens is the way to go. Then in terms of back caps, there's different sizes here, depending on whether or not, you need the clearance when you're fabricating. If there's, tight little spaces and you're trying to weld around a pipe or something like that, you might need to go to a shorter stubby back cap or even a button cap, but then that limits the overall length of the electrode that you can use. Then you have to start cutting these down to smaller lengths so that they'll fit in your back cap. Okay, so I'm going to show you how to put together your torch. A lot of people will put their collet body or their gas lens into their ceramic cup first and then put it screw it down onto the torch. I don't like to do it that way. I like to take the collet body or the gas lens and screw that down first so that you know that it's nice and snug to your insulator here and that there's no gaps in there that air can start to get in and get delivered to your weld pool and cause porosity and stuff. So I just make sure that that's nice and snug, just hand tight. You don't need to wrench down on this or anything. It's just going to damage the component. And then you'll take your ceramic cup and put it over that. Same thing, just tighten that down until it's nice and snug. And then you're going to take your electrode and your collet. So that's one thing I skipped over there. This is your collet. And the collet is the item that fits over the electrode. It tightens down on the electrode, and then it also transfers current to the electrode. So they come in, and there's basically two different designs. This one has the slit in the front and a little step in the back. Make sure that this is going towards the back of the torch, towards the back cap. Otherwise, it won't clamp down on your tungsten. But there is a different kind that has a angled piece in the front, which are a little bit more durable. A lot of people like those too, but this is what you'll see a lot of the time is this type. And so then you just take your tungsten electrode, and again, this goes towards the back of the torch. Go inside there, and then you can set your stick out however much you want for your stick out of your tungsten electrode, which is typically about 2 to 2.5 times the diameter of the electrode, is pretty standard. Then you'll take your back cap and you'll put that on here, and tightening down the back cap is what actually clamps it down onto that tungsten so that it won't slide. If you tighten this down and your electrode is still sliding around, that typically means that you have your collet backwards. Okay, so that's your collet. This gets referred to a lot as that thingy, this, if you can't remember what to call it, it's probably the collet. Get it? It's my collet joke. Anyway, so that's the components of a torch, and that's how to put it together, and hopefully that's helpful for you. Okay, so now we're going to talk about tungsten electrodes and filler metals, as well as the prep on your tungsten electrodes. So tungsten electrodes come in a variety of different alloy types or oxide types, excuse me, and that's just an additional element that is added to the tungstens that give them different properties. So there's a variety of different ones. This one would be serrated, lanthanated, thoriated, zirconiated, pure. There's also more proprietary blends out there that are like trimixes that are out on the market now. And they all have different properties. Some are better for others, for specific uses. Some are better for welding on steel. Some are better at lower amperages. Some are better at higher amperages. So I'm not going to get too much into the advantages of each one. I'm just going to talk about the electrode classification and what to look out for if you're a beginner. Typically the different oxide types that we have different types of, they'll have a different color on the electrode itself, so that if they're loose in a box or something like that, you don't lose track of what's what. And so all of these different oxide types have an associated color band that will come with them. So the electrode classification for an electrode, for a tungsten electrode, would look like this. And basically what we have is the E here stands for electrode. Okay, this is a current carrying electrode, meaning that that it is the electrode, but that the current actually goes through it. The W, this one is a little tricky because the W actually stands for Wolfram. I think I'm spelling that right, but I'm not quite sure, but this is German for tungsten. Okay, and we still haven't changed that. It's still a W. So anytime that you see W, you know that we're talking about a non-consumable tungsten electrode. Now the next two letters would be the type of alloy that or I keep saying alloy, but it's actually oxide type that the tungsten electrode is, okay? And then the last number here would be the percentage. So we could have a 1 or a 2, and this is just the percentage of that oxide that's added to the electrode. So for, say, a pure tungsten electrode, that means that there's no oxide added to it. So it's just pure tungsten. We used to use those a lot when we had our old sine wave type of AC machines, where when we were welding like aluminum, we need to ball up the end of the tungsten. So we'd use the green banded pure electrode for those. Not so much anymore now that we're using inverter machines that have a square wave type sine wave. I won't get into that too much just now, but that's the reason why we aren't using pure tungsten as much anymore. We're using some other different types. The one other thing that I wanted to say about the type of tungsten electrodes and the colors is that the red band, which it's red for a reason, kind of give you a little bit of caution, is a thoriated tungsten. So the oxide type that's thoriated is actually radioactive. So when grinding these, you need to take care not to breathe in any of the grinding dust because it can be a carcinogen. And so for that reason, we don't use these in the schools anymore, and typically just industry shies away from them now because they are radioactive and the grinding dust can be harmful. They were really well performing tungsten though. They're really, they resist contamination if you dip the weld pool and that sort of thing. So, back in the day, I really did like my thoriated tungstens. I still do like them, but now that there's other options, like I use trimix now, like a Z3 or something like that, on carbon steel and on pipe instead of a thoriated tungsten, and they're almost just as good. So there's other options there that aren't carcinogens as much as a thoriated tungsten. So if you see red color band, make sure that you're taking care with that because they are radioactive. Okay, so that's the tungsten electrode classification. Again, anytime you see that W, you know that it's a tungsten, a non-consumable tungsten electrode. The next thing I wanted to talk about is the prep on a tungsten. So typically the standard prep would be about a 30-degree bevel on that, that you're grinding the tungsten so that it's got a nice gradual slope to it. That's going to give you a weld bead that's not too wide, not too narrow. Just gives you good coverage of your arc. And then typically I'll put a little flat at the end. If you were to grind this all the way down, then you take a look at it with the microscope. At the very end, it will actually have a little curve where it like curls, which causes the arc to be a little bit uneven. So if you take and you just barely touch that wheel at the end to put a slight flat on the end, then it'll be nice and even on both sides. Now, if you want to, when we, beyond this 30-degree bevel, if we want to, put an extremely long point on it or a more stubby point, that's going to give you different properties as far as the width of your arc and that sort of thing. It's actually kind of the opposite of what you'd think. If you have a very long point here, then it's going to give you a wider cone. So it's good for, like a lot of people like it, open root pipe. So it's not focusing all the heat right in the center of that opening. It's kind of spreading it out, fanning it out. Where if you need something that's very, very focused on the arc, that's where you would make this more stubby, more of an abrupt angle. So that's two ways that you can change the shape of your weld bead or the arc cone itself. Okay, one other important thing, we always want our grinding marks to go lengthwise. Okay, so we don't want radial grinding marks on there because that creates ridges going around that will just give the tungsten opportunity as it expands and contracts with the heat to just pop off and end up with a tungsten inclusion in there. So we want the grinding marks to go lengthwise. So if you're using a radial wheel and you're grinding your tungsten on that, you wouldn't want to go to the side. You'd want to hold it straight up and down and turn your tungsten so that the grinding marks go lengthwise. Okay, so that's tungsten prep. The next thing that we'll talk about is filler metals. So the interesting thing about filler metals for TIG welding is that if you look at the classifications themselves, you may notice that it looks a little bit familiar if you're already familiar with the classification for GTAW electrodes, like wire on rolls. It's basically the same wire. So for instance, AWS A5.18 is the specification for carbon steel electrode and rods for gas shielded arc welding. So that means that both GTAW wire spools and GTAW pre-cut rod lengths for TIG welding are the exact same. If they have the exact same classification, that means that they're exactly the same metal, the same material with the same mechanical properties. So there's been times when I ran out of ER70S-6, I'm welding something in the shop here, and I ran out of my pre-cut lengths, and I can just cut some wire off, maybe braid it together to be able to get through a job and finish it, okay? Because it's the same exact type of material. So A5.18, the classification system looks like this. We have an E, which is electrode, current carrying electrode, or rod, ER, right? So it could be a wire electrode, or it could be a pre-cut length of rod, either one. The next two numbers here is the tensile strength in KSI, which means thousandths of PSI. So this would be 70,000 PSI tensile strength. So that's the minimum amount of tensile strength that this weld metal, this filler metal has in terms of when they pull a sample of it, to failure. It will have at least 70,000 tensile strength, okay? And that's really important to be able to overmatch the material that we're welding on. So again, 70,000 PSI. The next letter here is an S, which means that it's solid. Okay, it doesn't have any flux. It's not hollowed out. It's not a metal core wire or rod or anything like that. So it's a solid metal electrode or rod. And then the last one here would stand for the chemical composition, so some sort of alloying element that they add to it. In this case, the 6 is silica, which just adds a little bit more of weldability to the filler metal itself. It's actually that brown little glassy stuff that you see come up to the surface, especially when you're MIG welding. A lot of people ask me if that's normal. What is that stuff? Is it contamination? It's just the silica that's melting up, that is kind of coming up to the surface, which is a good sign. It means you got a nice hot weld. And that actually adds weldability. It makes the weld pool more fluid and helps with that. But there's all different kinds of numbers that have different alloying elements that they add to the weld to give different qualities. So that's what that means in terms of your filler metal composition. And then, of course, if we're welding stainless or something like that, we have that same ER, current carrying electrode or rod. And then these numbers would be for the series of stainless that it is. 308 would get matched up to 304. 316 is typically a little more resistant to corrosion for, food applications or marine applications, stuff like that. So you'd match that up with the base material 316. And 309 is typically used for dissimilar metals, like attaching carbon steel to stainless steel. But basically what I wanted you to see is that this electrode or rod, that it can be used for both GMAW and GTAW. So that's your filler metal classification to be used along with your electrode classification for GTAW.